Okay, that's there. Alrighty, let's go ahead and get started. While Oz chokes to death back there. Relax, little dude. You'll be okay. Alrighty, so we're going to talk about solutions today and tomorrow, and we'll see how far we get. So solutions, first off, we should probably throw up a definition for those. Solutions are always going to be homogeneous mixtures. I guess I forgot an E in there, didn't I? Which, as we remember, maybe from chapter 1, something like that, that those mean they're constant throughout, right? They have uniform composition. So solutions will have at least two parts. They must have at least one solute and one solvent. So you can have multiple solutes, but still only one solvent. I'm going to describe the solvent first. This is going to be the component with the most moles. It's what stuff is dissolving in. And so often we can think of solutions as something like salt water. Water is going to be your solvent there. So very often the water is a solvent. So it's the stuff that you are dissolving stuff into. So solutes, on the other hand, are what is being dissolved. So if we were to think of salt water, we have here a solute and a solvent. So just some terminology there. We can totally have multiple solutes, does not matter. You can have hundreds of solutes. For example, like your blood plasma has all these different proteins in it. It's got salt, it's got a little bit of potassium, it's got a little bit of calcium, actually not too much of the calcium side, but various other ions and things, as well as many different proteins and glucose and hormones and all this other stuff. So you can have tons of solutes, but only one solvent. So let me just write that out. Can have as many solutes as you want, but only one solvent. And so just so we are clear, the solvent is whatever there is the most of. And a lot of biology, in fact, pretty much all of biology, the solvent is going to be water. For chemistry, at least for general chemistry, typically your solvent is going to be water as well, but we're going to see we have some other kind of things going on here. Or at least right now we can have things that we talk about that are solutions that we can identify the solute and solvent for. So one more thing to note is that the physical properties of solution, that is not how we spell properties. The physical properties of the solution are most similar to the solvent. So if we think of salt water, and we want to think, is this more similar to pure water or is it more similar to salt? We can probably tell right away, okay, salt water is still liquid, it's still clear, it still boils roughly at 0 and 100 degrees Celsius, or freezes at 0, boils at 100. We're going to actually calculate what it would be. But, it's obviously much more similar to water than it is to salt, right? Salt would be, something that is melting at 3,000 degrees Celsius, and it's a white solid that's crystalline, obviously very different than a salt water would be. Alrighty, so here is a solution. So, based on what we know about air, if anyone remembers, what's the solvent going to be for air? So, while you're coming up with that, solutions don't need to be, solids dissolved in liquids. You could have any state dissolved in any other state. So, air is a solution that is just made up entirely of gases. So, what do we think the solvent is going to be in air? Perhaps we've forgotten. Oh my gosh, I can't write any numbers. So if this is our composition of air, which one is going to be the solvent? Yeah, nitrogen, exactly. Because that one is present the most, right? So 78% of air is nitrogen, so therefore nitrogen would be our solvent. And therefore our solutes are going to be everything else. So that could be oxygen, it could be argon, and it could be all those other trace gases as well. It could be carbon dioxide, water, methane, ozone, whatever. You could have tons of solutes. So any of these random other molecules in there would fall under this category. Maybe there's some ammonia too. Why not? Okay, so the solvent is always going to be just one thing, and it has to be the thing that's present in the biggest quantity. How about vodka? Vodka is roughly 40% ethanol and 60% water. So what do we think is going to be our solvent for the vodka? Hi, Gumbo. What you doing down there? What do we think, Sherry? Or other people? Yeah, it's going to be water, right? And so our solute would be the ethanol. In there. Yeah, exactly. So, hopefully not too bad. There's another. How about this one? How about something like steel? And I'm gonna just tell you it's carbon plus iron. Let's just say it's carbon and iron. And I'm not gonna tell you the percentages, but based on what you know of the properties of steel versus the properties of carbon and iron, which one do we think is going to be the solvent here? So remembering that the solvent will have, or rather the solution will have properties more similar to the solvent. So which one do we think that one's going to be? Oops. So let's think about some physical properties of steel. is steel metallic, or is it kind of like a brittle solid that we would use to write with, or something, or charcoal? Does steel burn pretty easily? What do we think here? Yeah, it's going to be more similar to iron, right? So even without knowing the percentages, whichever one is more similar to your solution is going to be your solvent, right? So steel is metallic and shiny-ish, and good conductor of heat, and it's very dense. Carbon is pretty brittle, and it's doesn't conduct very well, and it like will be flammable and all that fun stuff. So, and iron is going to share those similar properties of being metallic and conductive and all that stuff. So, iron is going to be our solvent there. Cool. Alrighty, so hopefully that should not be too much of a problem. Okay, so now that we've been able to kind of identify um, certain components of solutions, we can also talk about how many there are in a particular solution. And we refer to that as something called concentration. And that is how much of a solute is dissolved in your solution. And oh, okay, well, we see you now. Awesome. Welcome back, Lamando. I don't think I've ever logged out of Twitch. Interesting. Okay, anyways. So there's a number of ways to calculate this, or things we'll talk about. However, the one we're going to deal with in chemistry most often is one called molarity. And that is represented by a capital M, which is the moles of solute over the liters of solution. And it's just a way of describing, again, how much solute we have in our solution. And so this is this could also be called a molar concentration. But very often people just call it molarity. So I guess it's technically more accurate to call it a molar concentration, but that's a long word. I don't want to write it all the time. So this is how we're going to be kind of using molarity here. So again, molarity is going to be your moles of whatever your solute is over your liters of solution. For the purposes of our class, very often you're going to see that the liters of solvent and liters of solution will either be the same, or you'll be told what the differences would be. So let's go ahead and do a few. What's the molarity of a solution of So we're going to have 0.425 moles of calcium chloride dissolved to a total volume of 750 milliliters. So we have two numbers here. Our kind of equation is giving us, basically we just need to put moles and divide it by liters, right? So the moles, it looks like we have already. This first number is already in moles, so we're okay with that. However, this number here is in a technically incorrect unit for us. So we would want to make that into liters. Hopefully by now, going from milli to regular is not something that I have to write out every time for you guys. Just divide it by 1,000. It's very common to do that. I'll show you once, but for the rest of this chapter, I'm not gonna show you step by step for milliliters to liters. Hooray! There we go. So metric prefixes, old news by now. So, oh, look at this. I'm just a floating head. There, we'll go a little bit better. Okay. So the molarity of this solution would be R moles over R liters. Let's do the math. 0.425 divided by 0.75 is 0.56666666 forever. Looking at sig figs here, it looks like we're going to want 3. So this would be best described as 0.567 molar. If we wanted to be more precise, we would probably say, it's something like this, or something like that. So remembering that molarity, the capital M, has the units of moles per liter, we could just leave it as moles per liter as well. So in 2 chapters, we're going to be doing this pretty often where we want it in moles per liter. So either way would work. They both are equivalent to each other. We would understand it either way. Okay, so that's one way of doing it. So if we want to try another one, let's say now we have 30 grams of aluminum nitrate. Dissolved to a final volume of 100 ml. We could calculate the molarity of this. Remember that molarity is moles over liters. However, in this word problem, we have neither moles nor liters, right? So we do have something that we can convert to liters, and we do have something that we can convert to moles. Which one is going to be the one we're going to convert to moles? Yeah, we're going to want to make our grams into moles, right? So for this, that's just 0.1 liters. But for our 30 grams, I have looked up the molar mass while you guys were thinking. That's going to be 212. Actually, it's going to be 213. So that's 30 divided by 213. Oops. Apparently I need to put numlock on. So that tells us we have 0.1408 moles of aluminum nitrate. And so the molarity is going to be that number of moles. I'll put my sig fig marker there, over R liters. And so that will be a 1.41 molar solution of aluminum nitrate. Awesome. So when calculating molarity, you just got to make sure your stuff is in the right units and you'll be good to go. Pretty simple. Just put the moles over the liters. Note, because this thing does have 2 units, it is a conversion factor, so we could use it like that. What is a fun solute to use? How about let's see, in 50 milliliters of 1.25 molar copper 2 acetate. I'm going to look up the molar mass for that. I don't know why I keep coming up with compounds that have nasty molar masses to calculate. Okay, here it is. The molar mass is 181.63. So we're trying to see now how many grams we have if we're given a volume and a concentration. And so remembering that this number here is the same as moles per liter, we can do this kind of giant conversion, right? We're essentially going from milliliters to grams. And so we know that we can go moles to grams, right? We're going to have we have our molar mass there to do that. But our conversion factor here is moles per liter. So in fact, we're going to need to convert this to liters before we can convert it to moles. And so this would be kind of the plan for how we would do this unit conversion. And so we know, this is just 1,000, right, for the conversion there. We have the molar mass is going to be our conversion there. And this one is going to be our molarity. Are the 3 conversions we're going to need here. So if we start with our 50 mLs, we can go ahead and do our metric part to get it into liters. We could then use our molarity. Notice that because liters was on top, we're putting liters on the bottom here, just like any other unit conversion. And then the last one, of course, was our molar mass. And as always, for good practice, we should make sure that our units are canceling out. That's how we know we are doing this correctly. Liters cancel, moles cancel, we're left with grams. That is indeed what we want. So let's go ahead and see. So 50 divided by 1,000 times 1.25 times 181.63. Doing all this stuff, we get 11.4 grams. of copper 2 acetate. Don't let me keep choosing these complicated ions. This copper 2 chloride would have been so much easier. Oh well. So is this one okay? So again, just a word problem here. You could have solved it kind of using the moles per liter formula and then just did your molar mass afterwards. I'm always a fan of doing it in this, concise unit conversion type of pathway. But if you like to use, the formulas and stuff, totally okay. Go right ahead. Okie dokie. There's another one that I don't like to teach, but I'll teach it to you anyway. It's going to be percent solution. So this is often written percent weight per weight, which is something called weight percent, I guess. You have different types. You have weight per volume, volume per volume. Who cares? Those are kind of not common at all. So weight percent is going to be your mass of solute over the mass of solution. And since it's a percent, we're going to go ahead and throw that percent, 100% there as well. Mass of solution, just so we know, is your mass of all your solutes plus your mass of solvent. So in medicine, of course, we see 0.9% sodium chloride is our normal saline, right? That is the IV drip you're giving someone who is dehydrated, or if you need to dissolve drugs in it, you would be putting it into normal saline as well. So this is one scenario where this is pretty common. It's not really a very good way of describing these sorts of solutions. It's easy for pharmacists and stuff to make because the masses are already told to us, but it's a lot harder to do calculations with. So in chemistry, we don't typically use this. So biology and healthcare, you will use percentages, several, here and there, but not so much in chemistry. So I'll let you deal with those in bio class. But let's figure out what this is going to be. I'm going to just say 1 kilogram instead. Just make it easy on you guys. This is the only one we're going to do of percentages, by the way, because I don't like them. So it'll be there, but that's it. So 0.9% means the mass of sodium chloride, in this case we're given 1 kilogram, is going to be our solution mass. And so if we go ahead and do the math here, we're going to get that we have, let me see, converting this to percent, we have 0.009 grams of sodium chloride. This seems really small, but perhaps that's what it is. But it seems really small. Is normal saline 0.9%? Is that right? That number was in my head, but I'm not sure. Let's see. Normal saline. Let's find out. Yeah, it's 0.9%. Okay, well, so then that's what it would be. is so 0.009 grams would be our magic number there. So that is going to be, again, the concentration that you're going to be giving in the IV. Okay, awesome. I'm glad you guys know this better than I do. So awesome. So there we go. So you would, if you were in charge of making the saline, if you were in the saline factory, it's going to be 0.009%. So you would use 9 milligrams of sodium chloride in your kilogram of solution. Wait a second, I know it's wrong. Ho ho. Actually, that's okay. We'll leave it as that. I put it as a kilogram of solution, but it probably would have been a little bit better to... You know what? Let's forget it. We're good. 9.009 grams. Dissolve that in your 1 kilogram. You're good to go. That is your thingy. I guess I should be good about this, but I don't want to. Okay, so we need to technically have these in the same units. So this would technically be 1,000 grams instead. So what this is saying is that we actually need 9 grams of sodium chloride per 1,000 grams of solution. That would make more sense. Yeah. So technically you need your units to cancel out. So if we wanted to find grams of sodium chloride, we would actually need grams of solution. So technically this number here that we calculated was kilograms. And that's why it seems so small to me. And so that's why it would be the same thing as saying 9 grams per 1,000 grams of solution, because it's 0.009 kilograms. So that would be our answer there. So your unit should cancel out. So that's why it's 9.009 kilograms. Cool. Hooray! Yeah, I was going to say it seems real small to have 0.009 grams. So, awesome. Alrighty. Cool. Then, let's talk about how stuff actually dissolves now. Yeah, of course. Yeah, everybody makes mistakes. So, but I guess my experience is what tells me, like, hey, this doesn't seem right. That's that's when I know I've done something wrong. So, but yeah. Alrighty. So, let's go ahead and talk about how things dissolve. So this is where we're going to see those ion dipole forces coming into play here. So kind of our first scenario is ionic compounds. So what actually happens here is going to be our salt crystal. Nicely alternating, sodiums and chlorides in there. Lovely crystal. The water molecules are going to kind of come around it, and they're going to essentially like pluck off little ions at a time. And so we're going to see that we're going to have water molecules kind of surrounding each of the ions. And we're going to see that having all of these water molecules kind of hydrogen bond with our ions will make that ion dipole interaction, right? So the positive half of water, positive ions are, dealing with the negative half of water. And negative ions interact with the little positive part of water. Just so we are familiar, that is going to be the oxygen here, and that's going to be the hydrogen on that side. So that's essentially what's happening here. So we're just surrounding these ions with water molecules. They end up forming these very nice, favorable kind of connections, shall we say, to our ions. The ion dipole interaction, nice and strong. And we're going to see that we're going to just kind of get these ions surrounded by water molecules. And that is going to help remove them from their crystals that they're in. So, and we're going to have this for every single molecule. So, with that in mind, a substance, an ionic substance, let me just make that more clear, will dissolve in water if the ions prefer the water to each other. We're going to see in the next, or is that in this chapter? I don't remember if we talk about solubility of ions in this chapter. I'll check that. But we can see that sodium chloride, when dissolved, will break apart into its ions, and the water molecules are going to surround it. So we're going to see that this is soluble. We're going to have a few of them. For example, calcium carbonate is insoluble. That one is not going to break up into its ions. That is a no, not going to happen. Because the calcium ions really like the carbonate ions. They like them so much that the water is not going to be able to split them apart. So it all comes down to is the attraction to each other, the ions, are they attracted to each other enough that they can overcome this idea of water interacting with them. And so something that is soluble, the water is strong enough to break them apart. If it's insoluble, the ions prefer to stick together. And so we're going to see that that's kind of physically what's happening here. However, there are ways we can try and force things to happen. How can we make something dissolve faster? So it is time for your beverage in the afternoon or whatever. Let's say you're having iced tea, and you like your iced tea a little bit on the sweet side. So if you wanted to dissolve some sugar into your iced tea, how might you get it to dissolve faster? So normally if you just pour your sugar in the iced tea, it's going to just sit at the bottom for a very long time. It'll eventually dissolve on its own, but that would be like hours and hours. Yeah, so there's definitely one way. We can definitely heat it up. That's one way. What else can we do? Heating up is probably the most efficient, but stirring it would be another one. And so there's actually another one. We could also crush the solute into small particles. So when we are making our iced tea, if we put rock candy in there for whatever reason, that's the only sugar we have, that would just take forever, right? But if we have very finely granulated sugar, that will dissolve faster. So if you had super fine sugar or something, that's going to be able to dissolve in our liquid much more easily than something like rock candy, which would take a long time. So we kind of have three ways here, and they all kind of help the water to get in there. So by heating it up, that's making the water molecules move faster, right? And so as they move faster, it's just the chance of them kind of hitting this crystal and pulling off an ion, or in the case of a sugar, a molecule, is just higher. So the more energy you're giving them, the more likely they're going to be able to pick up one of your solutes and dissolve it. When you're stirring it, as you can imagine, what's happening here, these ions are being surrounded by the water. If we think what's happening nearby is eventually all the water molecules nearby will already have ions with them. And so by stirring it, we're kind of bringing in a fresh supply of new water molecules that do not have ions with them. And so then those new water molecules are going to be able to come in and pluck off some ions. Again, slowly over time, this process would happen by itself. The water would diffuse away, new water would come in, but that's pretty slow. If you take a drop of food coloring and put it in water, and don't touch it, eventually it will spread out to the entire thing, but that takes a very long time. If you were to just stir it once or twice, you'd get it to completely mix perfectly. Don't know if you could hear the barking, but we'll not take our chances there. Alrighty, and then the last one would be crush it into small particles. If you think about this crystal here, the water has to get all the stuff on the outside before it can start getting stuff on the inside, right? Like all this stuff on the outside is going to have to go away before new water can come in and take those crystals away. So the smaller crystals we have, it's just going to be faster because we don't have to wait for all these outside layers to get dissolved before we can get the whole thing dissolved. So if we break this in half, we're basically creating more surface area for new water to come and to come on in. So if we here's our water kind of coming in to try and grab ions. If we break this in half, now we can have more water molecules come in and start dissolving stuff on both sides. So that is what crushing the solute would do. It would break it apart so that more water molecules can come in and, grab them up. And so thankfully you already know this from real life. You already know how to get these things to dissolve faster, and perhaps now you know a bit more of a molecular explanation as to what is happening here. So those would be three ways to make something dissolve faster. One more thing you could do, you could also just add more water. That would also help to dissolve things faster because you're just kind of increasing the chances of like a fresh water supply coming in to start breaking up your ions. So that would technically be another way, but it's not something you would probably do to your iced tea. So, though what you could do with your iced tea is dissolve your sugar in hot water and then add it to your iced tea like a simple syrup or something, and that would get the job done. So technically, adding more solvent would also help, but that's probably less common because you typically already want your particular concentration. Like if you add more water to your tea, it's going to dilute it, right? It's going to make it less concentrated, so it'll have less flavor and all that fun stuff. Or not fun stuff. Cool. So that's how stuff dissolves. Another bit of fun stuff that we're going to talk about is when ionic compounds dissolve, they conduct electricity very strongly. So if you have the choice of unfortunately being stuck out in a thunderstorm and you really have to go swimming, um, don't do that, please, by the way. Um, it would be better to swim in like a freshwater supply than it would be to swim in like the ocean. Just because the salt in the ocean allows it to conduct electricity much, much better. And so that would be very bad for you if the electricity nearby or the water nearby has ions in it. So, by the way, please don't go swimming in a lightning storm. I know we don't really have those in California, but don't do it. Anyways, therefore, we call them strong electrolytes. So, light, as we know from biology, lysis, is breaking apart, right? So when you have like hemolysis or whatever, that's when your blood cells are bursting open or breaking apart. You know, all this lysis stuff talks about breaking. Glycolysis, breaking of glucose, all that stuff. And of course, electro has to deal with electricity. And so what this word actually means is it describes when or substances that conduct electricity when broken apart. So all of these ions there, because they're charged, they allow electrons to kind of hop around very quickly as it becomes attracted or repelled to the ions. And so that's why it is causing this electricity to be conducted. And we're going to see that all soluble ionic compounds are strong electrolytes. So something like sodium chloride would completely break apart into its ions when we dissolve it. Calcium chloride would also do the same thing. And something like aluminum chloride, guess what? Also, is gonna, when it dissolves, it's also gonna break apart. If we compare these, though, we could see we have 2 ions formed, 3 ions formed, and 4 ions formed in this case. We're going to see that this would conduct the best of the 3 of them. All 3 of them will conduct very strongly, but of these 3, the aluminum chloride is going to conduct the most because it has the most ions in there. So the number of ions is something that we're going to look at later on in this chapter. I figured I'd introduce it now. Will have some effect on some of the properties. So the number of ions does matter later on. For right now, just introducing strong electrolytes. Everything that is an ionic compound that is soluble will be a strong electrolyte. Okay. And so the more ions you have, of course, the stronger your conductivity is going to be, just because you have more places for electrons to hop around to. So the more ions you have, the more conductive your solution is going to be. All right, we have 6 acids also. And these are ones you will probably want to commit to memory or again have the post-it note so you know which ones they are. We have 3 of these halogen-based acids. We have sulfuric acid, perchloric acid, and nitric acid. So these 6, which you will want to learn, are called strong acids. And they break apart completely in water. So HCl, when we dissolve it, is really H plus and Cl minus. Because it is a strong electrolyte, it will break apart completely. So the water will separate the H off the Cls, and they'll be, doing their own, ion dipole interaction type thing. All right, we're going to see that all other acids are weak acids, meaning they only dissociate a little bit. So if we were to put a bunch of acetic acids or phosphoric acid or whatever your favorite acid is, most of them, I know I'm kind of drawing it as if it were a solid, but here, I'll make this a bit more crazy. They're liquids. Maybe one of these would be broken up. It's that blue one. That's the one that's broken up. So if we think about acetic acid, we're going to see that about 99% of the acetic acid is going to be formed or stay as that molecule and not break apart. And about 1% of the acetic acid will actually break apart. So previously, we had 100% of the acid breaking apart. But for weak acids, we're going to see that they only break apart a little bit. Maybe one molecule will break apart out of 100. And, it'll come together and another molecule will break apart. But by and large, if you were to kind of snapshot what this is looking like, you're going to see most of it does not break apart. So it will dissolve, but it will not break apart. And as we can see here, we have ions on this side, but no ions on the other side. And so we're going to see that this only very weakly conducts electrolytes, or electricity, rather. And so these are called, they are weak electrolytes. Again, only because a little bit of them break apart. So strong electrolytes, they completely break apart. Every single sodium chloride will break into a sodium and a chloride ion. For your weak acids, only a little bit will break apart. They'll still dissolve, but they will not break apart. Okay, so that is going to be every acid except for these 6. These 6 are going to be your strong acids. Every other acid you could possibly think of is going to be a weak acid. Okay, and it's only going to weakly conduct electricity. Okay, just have one more term to throw today, and that is something called a non-electrolyte. It will dissolve, but not break apart. So typically these are going to be polar molecular compounds. Man, I cannot spell today, can I? So this would be something like glucose, we know we can dissolve glucose in water. And if we do so, it's not actually going to conduct electricity because it does not break apart into ions. It stays as a glucose molecule. But because it's polar, we're not forming ion dipole interactions. We're just kind of forming hydrogen bonds or something. So these are not going to break apart into ions. This would also be something like ethanol, which we saw before, or formaldehyde. Something like that. These molecular compounds that are polar will dissolve in our water, but they're not going to form ions in the water. So they do not break apart. The molecules stay the way they are. They just kind of have, you've got your polar molecule or whatever. Here it is. Whatever it happens to be, I'm just putting a generic molecule. You're going to have your oxygens kind of hanging around the positive side, and your hydrogens hanging around the negative side, just like they were with ions, but since these are partial charges, it's not going to be as strong. Nothing is going to break apart. So every time you're going to see a polar molecular compound, that would be a non-electrolyte. Does not break apart, does not conduct electricity. So what we'll actually start with tomorrow is I'll show you evidence of all this stuff. So I'm going to show you various solutions. We're going to try and conduct electricity through them and see what happens. So this will be a video from the textbook. So just for the, if some of you don't have it or whatever, I'll show you what that looks like. So you can see kind of physically what's happening here. Alrighty, so we're pretty much out of time for today. So let's go ahead and I'm gonna right now put our poll in Discord for homework due Saturday or Sunday. Let's see, which fun little things shall we use this time? Let's have the which shapes shall we use? What are we thinking? How about, let's see, this yarn for Saturday. And what else? How about this? I don't want to use a teapot. Let's see something more fun. How about we use this cake for Sunday? Okay, so I'm going to go ahead and I'll show you the Discord so you can see what this is, but let me just put this yarn and cake so you can find them easily. Okay, so let's see, I think this is window 2, if I'm not mistaken. Is that Discord? Can you see it? Yeah, it looks like it. Okay, so for this week, if you want your homework due Saturday, you'll put the yarn, you'll click this yarn over here. If you want it due on Sunday, you're going to click the cake. Let me just make this a little bit more... that didn't help. Okay. So choose whichever one you want. If you want Sunday to have the time to look at the answer key, or if you just want to look at the answer key on Monday morning or something, then you could have it due Sunday. So whatever you guys want to do. Let me just go ahead and ping you guys so everybody can see it. So you'll have that. So it'll be under here under polls for your class. Just click the one that you want. Okay, so Maya, you can go ahead and if you want, click the cake, and then we'll have that. So hopefully by tomorrow we'll have some voting happening and people can choose what they want to do. I've preliminarily put it as Sunday for now, but we'll see if you guys change your minds or what's going to happen there. Okay, so I will see you all tomorrow. I did put up some homework for gas stuff yesterday. There's also a little bit of like an experiment. So there is a little short video that's going to have some data in it, as well as like a experiment data sheet for you guys to work on and do some calculations. So have fun with that. I will see you all tomorrow. Have a lovely day.